All right, so welcome to Math 409 problem solving. So this is lecture 5. And so what I want to do today is, if people had some, questions or additional comments they wanted to do on, sums of, on the arithmetic mean, geometric mean, inequality, let me know. I wanted to first talk a little bit more about sums of powers. I am keeping my cell phone not on silent because there's at least one person who is zooming in. We're going to have, unfortunately, a lot of people going through Zoom days as the semester progresses, and I just want to make sure if they have any comments or questions that I am able to hear it. So there are certain things where if you can solve, you get an A+ in this course, plus many, many other things. And we will get to some geometric problems later. Just to warn you, people have tried some of these, and a year later are still banging their head. It's not necessarily a bad idea to try problems like this, but these problems are hard. And so what I want to do is I want to talk a little bit about sums of powers and just throw the gauntlet down. And if you're able to do this, I will be very impressed. I'll be very happy. This will lead to a publication. So we talked about how to find the sums of the first n integers. And we have Gauss's trick, so this is really not that bad. Just write them in reverse order. That doesn't work for sums of squares, cubes, or higher powers. We saw that there was a very clever trick you could do to get sums of cubes just by knowing sums of first powers. And you can then ask, how far can you push something like this? And it turns out if you know sums of squares and sums of first powers, you can actually come up with a formula that gives you anything. So the question is, how can you derive formulas? Oh, it's not displaying. Okay. How can you derive formulas like this? Well, one of them is by induction. And what was the biggest obstacle to using induction to get formulas for sums of powers? Having the formula. So I'm going to show you a way that doesn't really require the formula. So the input that I need, and I love how it always greatly increases the thickness when I shift, is the geometric series formula. And so now we will reduce it to human thickness. Okay, so if we have 1 plus x squared plus ... plus x to the n, this is equal to 1 minus x to the n plus 1 over 1 minus x. Does anybody remember how to prove this? So, yep. So induction, I think, would work. And so we then have this formula, then you would add one more term. So induction should work. So induction is 1. Telescoping is my favorite. So if we let Sn be 1 plus x plus ... plus xn, if we multiply by x, we then get x plus ... plus xn minus 1. So if we subtract, we get 1 minus x times Sn is 1 minus x to the n minus 1. And that, of course, implies that Sn is 1 minus x to the n plus 1 over 1 minus x. And then as a nice corollary, if the absolute value of x is less than 1, then 1 plus x squared plus ... equals 1 over 1 minus x. Okay, so this is the geometric series formula. So we can use. You walk through that proof one more time. Sure. So we multiply the sum Sn by x. And now instead of having 1x all the way up to xn, we now have x squared all the way up to x to the n. Oh, there's a typo there. That might be the reason. Up to x to the n plus 1. So thank you.
And the 1 is
well, because we multiply every term by x. So the last term, I wrote minus 1 by mistake. It should be plus 1. So we have 1 plus x all the way up to xn originally. And since we multiply every term by x, we now have, instead of going from 1 to xn, we go from x to xn plus 1. And when we subtract, everything in the middle cancels. And we're left with just the first term and the last term. So when we subtract x minus x is 0, x squared minus x squared is 0, x to the n minus x to the n is 0, And we're left with just 1 minus x to the n plus 1. On the left-hand side, we get Sn minus x Sn. We can pull out the Sn and we just get 1 minus x. And so we now have a formula for finite geometric sum. Why is this useful? So to some extent, it's actually nice that we are teaching in a physics department, because physicists play fast and loose with the math. And so what I'm going to do today can be justified. In general, it requires a little bit of work. So one of the great results is differentiating under the integral or sum. So when can I switch the order of a differentiation and an integration, or a differentiation and a sum? So it's trivial if finite. The derivative of a finite sum is the finite sum of the derivatives, but it's not necessarily true if you have infinitely many terms. All right, so let's consider, Sn is 1 plus x squared plus dot 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 plus xn. Okay. And what I'm going to do is I'm going to apply the operator x d by dx to both sides. And the reason I'm going to apply x d by dx is that way each term, if it was x to the 5th, it ends as x to the 5th. So when I apply x d by dx to Sn, so I'll write it Sn of x, just really emphasize that it's a function of x. Well, what am I going to get? Derivative, bless you, derivative of 1 is 0. The derivative of x is, but then I multiply it by x, so I just get x. The derivative of x squared is, but then I multiply by x, so I get 2x squared, all the way down to nx to the n. But this is also equal to x d by dx of 1 minus x to the n plus 1 over 1 minus x. Right? How do we take the derivative? Oops. So how do we take the derivative? Quotient rule, right? Who here wants to use the quotient rule? No one wants to use the quotient rule, right? Now, is this a terrible quotient rule? So I like using mathematics. So I'll define f of x to be 1 minus x to the n plus 1 divided by 1 minus x. So it's a little, is this large enough that people can see? Okay. So it's a little bit hard for me to use the newest version of Mathematica. It's actually automatically putting in parentheses and whatnot. It's something that, it's wonderful, but when you're used to putting the parentheses, it's very easy to have too many. So now I'll just take the derivative of f of x with respect to x. And there we go. So this is how you do differentiation in the 21st century. You don't do it by hand. And I'll paste this into the slides later. Here's the derivative. Actually, I can probably just do it right now. I can just write it. And then, so we get, this is going to equal, it's 1 plus n x to the n over 1 minus x. Let me have a common denominator. So I'll multiply this by 1 minus x. And then we have plus a 1 minus x to the, that's 1 plus n, well, that's really the same as n plus 1, over 1 minus x squared. Okay, now this equals 1, well, I guess we're doing 0 plus 1 plus dot 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 plus n. And I got to put in my x's, plus 2x squared plus dot 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 plus n x to the n. So if these are equal, can anybody tell me a good thing to do now? Take x equals 1. Take x equals 1, and we have a formula for the sum of the first n integers, or n plus 1 if include 0. Wow, we have a formula. Now, when you look at the formula, what might be a problem about taking x equals 1? Denominator is 0. What about the numerator? So I've never done really limits in Mathematica. Limit. Oh, there's a negative sign. I missed the negative sign. Okay. So if we take the limit of our expression, I think it's x1.
Oh, no, that's right down.
Is it what?
Right
Is
down.
right arrow 1? Okay. Yeah, I was about to look up right arrow 1. And so if you then ask Mathematica to take the limit, it takes the limit and you get 1/2 nn plus 1, which is the correct answer. If you do not have access to Mathematica to take the limits, how would you take the limit of this? L'Hopital's rule. And so let me go back to sharing. So I will take over the screen share. So you know you've made it in mathematics when your name becomes a verb. So you L'Hopital it. Okay, so use L'Hopital and get the limit as x goes to 1. So what is L'Hopital's rule? So since it's possibly been a while for some people, so L'Hopital, if the limit as x goes to x naught of f of x over g of x is 0 over 0 or infinity over infinity, then it equals the limit as x goes to x naught of f prime of x over g prime of x. And if that's 0 over 0, infinity over infinity, what do you do? Same thing, L'Hopital, keep L'Hopitaling until you no longer have 0 over 0 or infinity over infinity. This is an extremely powerful method to prove things. So I'm going to just quickly sketch the proof. We'll assume x naught is finite, and we have 0 over 0. And the reason I want to show the proof is this proof highlights two of the best ideas in mathematics. So most of math is about doing nothing, but doing it in such a way that the algebra becomes more illuminating. So can somebody tell me a nothing I can do? Plus 0. What's the other nothing I can do? Times 1. And then my professor Peter Jones at Yale said, actually, the log of 1 is 0. So there's really only one thing you can do. So what we can do is we can write f of x over g of x as f of x, g of x. And then what I'm going to do is I'm going to subtract f of x naught and subtract g of x naught. Why can I do that? Well, I'm assuming I have 0 over 0. So this is, red is okay as f of x naught equals g of x naught is 0. And now I can divide by x minus x naught. Mean is okay as it's multiplying by 1. And so now, if I take the limit as x goes to x naught, this is, what is the numerator equal? F prime of x naught. This is one of the other ways of writing the definition of the derivative. So normally we would write x naught plus h. Well, just think of x as x naught plus h. So this is just going to be f prime of x naught over g prime of x naught. So this is a proof of L'Hopital's rule in the special case that x naught is finite and we have 0 over 0. It highlights some of the really great techniques we have in problem solving. In most problems, if you can find a clever way to add 0, if you can find a clever way to multiply by 1, you can often make things look a lot better. Okay, so now we have a formula for the sum of squares. I'm sorry, for the sum of integers to the first powers. So now let's look at maybe S2n of x. This is going to be 0 plus 1 squared x plus 2 squared x squared plus 3 squared x cubed plus dot 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 plus n squared x to the n. So I want to get something like that. So we start. Oh, that's interesting.
There's some delay.
The delay shouldn't be this bad. Thank you. So, all right, so let's go back to recording. Okay. So now we have Sn, which I think we rewrote as maybe Sn of x was 1 plus x plus dot 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 plus xn. Then we did x d by dx of Sn was 0 plus 1 times x plus 2 times x squared plus dot 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 plus n times x to the n. What should we do now? Do it again. So do x d by dx of x d by dx of Sn of x. And this is going to then be 0 plus 1 squared x plus 2 squared x squared plus dot 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 plus n squared x to the n. And this will be x d by dx of x d by dx of 1 minus x to the n plus 1 over 1 minus x. Okay, so going back to Mathematica, this is what we got when we got the first derivative. Well, I'll just take the derivative of f of x with respect to x and take the derivative of that with respect to x. And this is the expression we then get. And so what would we do with this expression? Oh, sorry, that's right. Thank you. Thank you. I need x. Thank you. I need, oh, so wait, over here, when I did the derivative, I didn't multiply by x. Thank you. So that needs to be fixed. So let me just go back a page and just make sure I put that in. It's actually not going to make a difference, that I dropped it in the first one, because we take x equals 1. So that was actually a very fine mistake to make. How many of you remember taking a class called multivariable calculus? You might have done parameterizations of curves and trying to talk about how far it's traveled and whatnot. You always parameterize to have unit speed, because then you don't have to remember, do I divide by the speed I'm traveling at? If you're traveling at a unit speed, you're never going to have to worry about that one causing trouble here. So I made a mistake, but fortunately it's a mistake that initially is not visible because I'm evaluating it at x equals 1. So I get a more involved expression here. And that's what I should be taking the limit of as x goes to 1. Do we do this properly?
X goes outside the derivative.
Oh, wait, oh, yeah, x goes outside the derivative. Thank you. I put it inside the derivative. Thank you. There you go. Good. And it should just be exactly, and this is why you always do checks to make sure you haven't made a mistake. Okay, there we go. Now we get back where we wanted. So we take the derivative of f with respect to x, and then we multiply that by x, and then we multiply on the outside by x. And now this is the expression we get. That's better. And now we take the limit of that as x goes to 1. Okay. Does that look right?
No.
So let's see, try simplify, because we need to know how things factor. So let's try factor. Okay, so we do factor, then it's 2n plus 1 times n plus 1 times n. That's right. So this is a way to find a formula for the sum of squares. All we needed as input was the finite geometric series formula. Could you find a formula for the sum of cubes using this method? Yes, right? Here's our function. We need to take the derivative of this with respect to x. And I think that's what we now get for sums of cubes. And now we use L'Hopital's rule. And then we can do fourth powers. So I actually wrote up the calculations using L'Hopital's rule to do sums of squares. I am convinced if my life depended on it, I could do cubes or fourth powers or any finite number. It's just a question of how long would it take me. So my question to you is, can you use L'Hopital's rule and prove what the formula is for the sum of, say, kth powers? If you can't, can you at least prove certain facts? Can you prove the following? That it's going to be a polynomial, that the degree is going to be 1 more than the degree you start. So if you're doing sums of degree, sums of dth powers, it'll be a polynomial of degree d plus 1. Can you prove the leading coefficient is 1 over d plus 1? Can you prove stuff like that? Or maybe you can't get all the coefficients, but can you show that this method will have to give you a polynomial of the right degree? So that is my challenge problem to you. And if you can do this, and if it hasn't been done, then I think this is actually a paper that can be published. This is not going to be a groundbreaking paper that will change the history of mathematics. But if anybody's interested in this, just write to me. And anybody who wants to, we can work on this. Can you find a good way to do the calculation? And again, this is a class in problem solving. My goal is not to overwhelm you with stuff to read. My goal is to have interactive class discussions with things to think about. If you can do something with this, that's wonderful. You can see very quickly this is becoming a nightmare. But is it a nightmare that at least has to simplify to a polynomial? Does it have to simplify to something nice? Can you prove that? And then what the actual values are, we don't know, but we at least know it's a polynomial. Is there anybody who doubts that the sun will rise tomorrow? I think I'm allowed to ask that question. Everybody's confident that the sun will rise tomorrow, yes? Okay, we don't have a proof of that, but we are basing our lives on the fact that the sun will rise tomorrow. When we're trying to come up with these formulas to do these proofs by induction for PowerSums, we can just, let's guess that it's a polynomial. And if the guess happens to work, great, we're in wonderful shape. And we can just go with that. So for a lot of things, you can often just make assumptions and see if it pans out. But could you make this rigorous? Can you prove that this will have to simplify? And I have some ideas on how to do this. I am deliberately not thinking about it, which is painful. But I'm leaving this as a problem to think about. Can you prove that it will be a polynomial? And if you can prove it's a polynomial, can you prove it will have the appropriate degree? And if you can prove it has the appropriate degree, can you prove that the leading term is 1 over d plus 1? And can you even go further and prove that the constant term is 0? All right, so I will paste the Mathematica stuff into the PowerPoint later. What I will do now is I will now try to recapture the share on the iPad. Okay, any questions on PowerSums? Okay. Okay, so we're good on PowerSums. And so the question is, can you generalize? Can you prove stuff in general? So I will leave that as a extra credit problem. Okay, the next thing is, did anybody else have any thoughts or any questions they wanted to talk about the arithmetic mean, geometric mean inequalities? So this is an absolutely beautiful subject. And a lot of times the question is, what's the best way to prove this? And so the video had a bunch of different proofs. Some of my favorites are, I can't remember what's in the video. Sometimes you prove it when n is a power of 2, and then you actually collapse downward, which is nice. Sometimes you try to induct upwards. We talked a little bit about trying to do special cases. So when we have the arithmetic mean of x1 through xn is x1 plus xn over n, and the geometric mean of x1 through xn is the nth root. Okay. And we might as well assume, my favorite logarithm without loss of generality, x1 dot 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 xn are greater than 0. You could even by symmetry assume that x1 is the smallest, x2 is the second smallest, and so on, but we'll leave it like this. So a lot of times, we might make some simplifying assumptions. Because the numbers are not 0, this gives us the ability to rescale. And so I want to talk about possible rescalings. If want, 0 less than x1 less than equal to x2 less than equal to xn. So can somebody give me one possible rescaling that I can do? Set which one? So one is xn equals 1. I can rescale so that the largest value is 1. And the reason is if I multiply everything by alpha, then the arithmetic mean increases by alpha and the geometric mean increases by alpha. So without loss of generality, I can always assume xn equals 1, rescale all by 1 over xn, which is not 0. Well, if you're going to do that, we could take x1 to be 1. What other rescales could we do? There's at least 2 more rescales. Product or sum. So we could do x1 plus xn equals what? What would you choose the sum to be? N or 1? To me, those are the only natural choices for the sum. Any other choice you have to fight with me as to why I should be willing to consider. But make the sum equal 1, that seems natural. Or make the sum equal n, so when you divide by n, it's good. And then the last one is x1 times xn equals what? What should we make the product? 1. And here for the product, I don't think there's any dispute about what value you want the product to be. I think it's natural to have the product equaling 1. And so this is a little bit of a simplification you could do. And then did the video do the Lagrange multipliers approach? Okay, let's do Lagrange multipliers. Whenever possible, I try to have 317 and 409 overlap so I can be doing the same material and I can test it out on 317 before coming here. How many of you remember, this is the multivariable calculus day, Lagrange multipliers? How many would like to remember Lagrange multipliers, or at least are willing to pretend that they want to multiply? So, again, good techniques. Lagrange multipliers. And if you want more on this, let me know and I can share with you some details from the video earlier today. So the way Lagrange multipliers work is I want to find the maximum or minimum of f of, say, x1 ... xn subject to g of x1 ... xn equals c. And the way it works is, here's my constraint. Here's, g of x equals c. Maybe here would be g of x equals c plus 1. Maybe here would be g of x equals c minus 1. And then the gradient of g is normal to the surface g of x equals c. And so if I give you, my gradient of my function f, I can break it down into two parts. Something, let's say something, tangent to the surface and something perpendicular. If you have a component that's tangent to the surface, if you just move in that direction, your function increases. If you move backwards, your function decreases. So you can't be a maximum on the constrained surface if your gradient has a non-zero component tangent to the surface. Or in other words, you need your gradient to be normal to the surface, which means the gradient has to be parallel to the normal. What does it mean to be parallel? It means the vectors are multiples of each other, and that's what the lambda is. So candidates for max or min have the gradient of f is parallel to the gradient of g. So gradient of f equals lambda gradient of g, and you still have g of x equals c. So now you have n+1 equations and n+1 unknowns. You have a chance of solving this. So Lagrange multipliers is an absolutely wonderful idea. So for us, for the AMGM, which do you want to do? Do you want to have the sum as your constraints, or do you want to have the product as the constraints? Sum? All right. And what do you want the sum to equal? Okay, so we'll have the sum equals n. So sum is n, and you want to find extrema of the product. All right, so we have g of x1 through xn is x1 plus ... plus xn over n equals 1, and f of x1 through xn equals x1 times xn. Is that okay? Any concerns about what I've just done? Yeah, I should have an nth root, but because g equals 1, if I raise f to the nth power and I raise g to the nth power, does it make a difference? So
why is g equal 1?
well, we said we wanted to adjust things so that it equals 1. What I'm worried now is maybe I do need to have an nth root here. If that's the original problem, can I just replace my function with the nth power? Or if I'm going to do that, do I have to have g to the nth power and then worry about a more complicated set of derivatives?
Nth root is a strictly increasing function. So yeah, I think the nth root is a strictly increasing function. So maximizing the nth root is the same as maximizing the function itself.
Right. And so we could then, at the end of the day, take the nth root. So we've got to be very, very careful when we have something like this as to, am I making any mistakes in dropping the nth root? And again, if the sum is equal to 1, if I take the nth power, that's still equal to 1. But it will change the derivatives, but it'll change the derivatives in a way that doesn't really matter. So if we then looked at, let's call it g tilde of x1 to xn, which would be x1 plus xn over n to the n, and f tilde x1 xn equals the product. When I take the derivatives of g, I'm just going to get n times that whole sum to the n minus 1 power, but that's going to equal 1. So it's not going to really matter. So I'm just going to do it the long way. It doesn't really matter. So the gradient of g is going to be n x1 plus dot 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 plus xn over n to the n minus 1. Every term has that. And now I go inside. What's the derivative of this with respect to x1? It's just going to be 1 over n. What's the derivative with respect to x2? It's just going to be 1 over n. So in fact, it will be, if I've done it correctly, 1 over n, and then the vector, that's all ones. And because of our constraint that this equals 1, this really just becomes the vector of all ones. So we were fine to just look at the nth power immediately. But just I want you to be aware of the dangers you have to be. What about the gradient of f tilde? So I want to take the derivative of x1 through xn. So what's the derivative of x1 through xn with respect to x1? I'm sorry?
Or just f tilde divided by f1.
Good. It's f tilde divided by x1. If I take the derivative with respect to x1, I just get x2, x3, x4 all the way to xn. That's the same as the whole product divided by x1. When I take the derivative with respect to x2, I lose the x2 term. It's the whole product divided by x2. So a great way of writing this is it's x1 dot 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 xn times 1 over x1 dot 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 1 over xn. I don't really care what lambda is. This whole thing is going to be affecting everything. And so when I play the games, I need to solve 1 over x1 dot 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 1 over xn equals lambda, and I'll say lambda depends on x1 through xn, 1 dot 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 1. Okay. This is really nice. I need the vector 1 over x1 through 1 over xn has to be a multiple of the vector 1, 1, 1, 1, 1. What can I conclude? All the x's have to be equal. If all the x's aren't equal, they're not going to be in the same direction. So we conclude x1 equals x2 equals dot 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 equals xn as their sum equals n. It implies each xk equals 1. So the only critical point is when all the x's are equal to 1. So this will either be the minimum or the maximum. Which do you think it is?
Because if one of the x's goes close to 0, then the geometrically goes to 0 as well.
So what we can do is we do special case. So use special case. So we have x1 plus xn over n, and we have the nth root of x1 through xn. As we send one of the x's to 0, the product goes to 0, but the sum is staying the same. Well, we've got to be careful. Maybe if one of the x's is going to 0, the other x's are getting large and the product is becoming huge. Well, we can do x3 equals dot 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 equals xn equals 1, and then maybe x1 equals now we've got to figure out how do we want to choose things. So we need to have two numbers that sum to 2, and we want the product to be really small.
epsilon and minus epsilon.
So I could do epsilon for x1, and x2 is 2 minus epsilon. So x1 times x2 is going to be epsilon 2 minus epsilon. That's less than or equal to 2 epsilon. That goes to 0. So by looking at an extreme case, we can see that we can make this product very, very small. Well, this is still staying 1. So since this was the minimum value, it's going to be like this. Why? Because we've chosen this so that this expression on the left is always 1. And so the minimum value, I'm sorry, the maximum value of this expression here is 1. So because this is always at most 1, then it has to be always less than or equal to the arithmetic mean, because the arithmetic mean is always 1. This is one of the great powers of being able to adjust the quantities we're looking at. Because we can adjust the quantities we're looking at, we can simplify a lot of things and say, okay, it's enough to reduce to this special case. For a lot of problems, the way we frequently do things is we try to build up from smaller cases. And so I'll leave a problem for you to think about, to report on for the next class. So here is the problem. And some of you might have seen this before in another class. Given some large number S, find x1 ... xn such that 1, each xi greater than or equal to 1 is an integer, and 2, x1 plus ... plus xn equals s, and 3, the product is as large as possible. So think about this for the next class. This is one of my absolute favorite problems. So I know I've done this in some classes. I might have done it in operations research a few years ago. It is solvable using almost everything in some early classes. So you're not required to use heavy machinery. The first thing you should always have in mind whenever you see something like this is look at the conditions I've imposed. So I want the x's to be integers. Okay, you could, of course, redo with each xi greater than 0 now real. And ask, how does the answer change if we go from trying to find the integer max to finding the real max?
There's no constraint on how many.
No constraint on how many. That's what makes this problem challenging. Is I'm not telling you in advance how many pieces to chop it into. You have the freedom of choosing how many chops you want. And once you choose the number of chops, you have a freedom of deciding how you want to allocate among the x's. Nope. So can somebody tell me why I'm not allowing the integers to be greater than or equal to 0? Why am I forcing the integers to be at least 1? So always look at the conditions and ask, why did they choose these conditions? What would happen if I allowed you to have some of the x's be 0?
Would it be just unwise for us to choose x's between 0 and 1?
Okay, so why would it be unwise to have one of the x's be 0?
You have to scale by each x.
Nope, not quite.
Would decrease the product?
Yeah, but what would happen to the product if one of the x's is 0? Yeah, can you give me something better? Yeah, just take x1 equals s, right? So clearly we know that the maximum is not going to happen when one of the x's is 0. So I'm giving you that much of a hint. What if we allowed some of the x's to be negative? What would happen if some of the x's were allowed to be negative? You could get arbitrarily large. So as a nice exercise, show that if you allow the x's to be negative or positive, you can make the product arbitrarily large. So these constraints are necessary to make the problem interesting and to eliminate smart-ass answers. So again, when you are doing a problem from, say, the Putnam or math competition, hopefully they've thought about the problem, hopefully they've checked to make sure, but usually they do a really good job of thinking about the conditions. And the conditions are usually chosen for a reason. So always ask yourself, why was this put in? So I think earlier today I mentioned Peter Jones from Yale. He gave me many wonderful pieces of advice over the years, took 3 classes from him. One of the best pieces of advice he ever gave me was, if you have a result that you think should be true, ask yourself, have you ever read about it? Have you seen a name attached to it? And in an old, well-established subject, if you have been working in it for a while, you should have seen it. And if you haven't, it's probably not true. So a lot of times, if you take some of the standard theorems and you remove a condition, it's no longer true. And so when I was taking my general exam at Princeton to get my master's, one of my questions in abstract algebra was, is the following a group? And it had a lot of the conditions of a group, but not all of them. And some of them were slightly tweaked. And being a paranoid, very scared graduate student, I had looked at a lot of books preparing for the general exam. I had read at least 6 different algebra books. And in all of those versions, I had never seen among the exercises or the alternate definitions, this as a group. And so I said, no, it's not a group. They go, good, correct. Now prove your assertion. Well, since it's not a group, all I have to do is find something that satisfies these conditions and is not a group. So it was a proof by construction. So again, this is a problem-solving class. The goal is to teach you how to attack problems. As soon as you see conditions, you should be asking yourself, why is that there? Sometimes it's there to mislead you. Has anybody described a red herring for this class? Anybody want to describe a red herring? Has nobody here heard the phrase red herring? It's a device intended to mislead. It's something irrelevant that makes you look at things the wrong way. My father got into trouble years ago with my mother at a party because he was talking to somebody and said that his wife is so old that her son from her first marriage is now in college. And so somebody went up to my mother and said, I didn't know you were married to someone before Bill. What? Is it wrong to say her son from her first marriage is in college if she's only been married once? No, but boy, did it mislead some people. So a lot of times in problems, they do try to trick you and they try to get you to think about the wrong thing. So over here, when I'm giving conditions, you should always be asking, is it crucial that it's an integer? Is it crucial that it's greater than or equal to 1? What would happen if it's greater than or equal to 0? What would happen if it's a general integer? Think about the different constraints. All right, so try to solve what's going on for the next class just in general when they're integers. And then if you can, try to redo it when the x's are real. All right, so this is a good place to stop. I can stop recording. Okay.